Today, let's talk about generalized additive models. It can be thought of as an extension of the generalized linear model, where the underlying function is a curve rather than a straight line. So today, we will see how we can combine the idea of generalized linear models and the Spline function into the generalized additive model. Okay, so here is a problem setup. Suppose we are given paired data points x and yi, where I goes from 1 to n. There are n data points. The xi are the predictors that lives in some p-dimensional space, and yi are the responses, scalars. So for the first problem, we would like to consider the yi to be Gaussian distributed. This has the same setup of the smoothing spline. So instead of just directly solving the optimization problem of the smoothing spline, we also want to write down a statistical model for it, where each of the parameters or the random variables are follow some distribution, right? So here we want to add a noise term epsilon I that is Gaussian distributed to this model, such as this f function here captures kind of the nonlinear relationship between x and y. Then the second case here, we would like to consider a more general distribution for yi that comes from the exponential family. So this is the setup for the GAM, right, for the generalized additive models. There are several distributions in the exponential family. For example, but the most common one are just three of them. The first one is the Gaussian. That's how we model the continuous distribution where y is real number, right? I should say is real number. The second distribution is Poisson, right? That's for the count data. When yi is a non-negative integer. So and the third one is a Bernoulli. So this is for binary data. Yi is that means yi is 0 or 1, right? So these are the three most common distribution we use for exponential family. Although there are other distribution out there, but they are rarely used. So next, this is how we set up for the GAM model. So see, this setup has very similar form with the generalized linear model, where the difference is that we're using a nonlinear function f of xi to capture the relationship with the mean of yi, right? So that is the difference with GLM. I should say that here for so fxi equals to xi transpose beta for GLM, right? But for GAM here, we use the nonlinear function to capture that. Okay, so in order to understand the generalized additive model, let's consider this roadmap in here, right? So we start with a linear model, and then we take two paths to generalize this, right? So the first path is that we want to generalize it into the spline, right? So this is when the linear model become nonlinear, right? So this is a nonlinear. And then we can also generalize it into the GLM, right? So this is a case where yi is non-Gaussian, right? Then for the GAM, it's really just to combine both ideas into one, right? So we just combine these two ideas into GAM, right? So that's how the model arises. And in terms of this video, let's just take the exact step in here. So the first thing that we're gonna do is to just do a review from the linear model to the spline function as we did for last time. Let's just quickly go over that. Then let's do another recap of the GLM model. After that, we'll just combine these two into the GAM models. So that's going to be the setup for this video. Okay, so now let's take a look at the first step here to see how we generalize the linear models into nonlinear curve fitting with the spline function. So for the linear model, the objective we have is this least square problem, whereas for the smoothing spline, we add a curvature penalty term besides this least square term. And then also for our nonlinear function fx, we can apply a basis expansion on the input x and then multiply that with the beta, right? So this is this is actually linear in the feature space, right? This is what we call the feature space for phi x. So it's linear in feature space, but it's nonlinear in X, right? I should say that feature space is phi of X. So that is the key of how we solve the smoothing spline. And then we also write down the matrix form to make things nicer, right? For the LM, so the matrix form is just going to be minimize of beta of y minus x beta transpose y minus x beta. And then for the smoothing span, remember what we did for last time? We have the minimize of beta, then we have y minus, we have the phi beta transpose y minus phi beta. Then we also have the curvature penalty as lambda times beta transpose omega beta, right? So that is the objective. Also, we think that in the last time, we also have the continuity condition, right? So we have the continuity condition written as A times beta equals to 0. But here, the interesting thing is that we can remove this continuity condition if we pick our basis function cleverly. So remember that the last time when we pick the basis function as this, right? When we have like multiple data points, right? Then we parameterize each piece with a cubic function, right? We have this cubic function f1 of x and then f2 of x for each piece. Then we use a direct parameterization, right? So that is a1 times x to the third plus b1 times x to the second power plus c1x plus d1, right? But that is not very smart, right? We can actually make this cubic function to be second derivative, to have the continuous second derivative. So we can just remove this term completely, right? So for example, a choice is just going to be the cubic span, right? It's cubic span basis. So that is defined as x minus xi absolute value to the third power, right? So this basis function, we can define n basis function with this, right? One at each data point. Then the second derivative is going to be continuous. So we can just remove the second term directly, but the curvature penalty here is still going to be the same form, right? As beta transpose omega beta. So the reason here being that if we just take the second derivative for this function, right? If we take the second derivative, that's going to give us a linear function. So this is going to be a linear function. So it's second, I should say second derivative is continuous and linear. Okay, then if we take a look at the curvature penalty here, so the second derivative will be linear. Then when we square it, that will be a quadratic function, which is exactly why we have this term as this quadratic form here as beta transpose omega beta. Right, so this omega beta here is depends on x, right? Depend on our, so this really should be just omega x. But you see that here that the omega x is just going to be fixed numbers, right? It's going to be a constant matrix given one particular problem. So that is the objective we are solving here, right? We're just solving a penalized least square problem for the spline function. For our generalized additive model, we're just going to carry this penalty term to the objective of the GAM models, but swap out the first term with the log likelihood, as we did for the generalized linear models. Okay, so for the second step, let's take a comparison between the linear model and generalized linear model. So for the linear model, it actually has a statistical interpretation for it, such that the response yi is Gaussian distributed. Then the expectation of the y is usually written as mu I here, and the mu I is connected to our predictor xi as xi transpose beta. Then for the generalized linear model, we would like to consider yi to follow some exponential family distribution. For here, we can still return the mu I as the expected value for the yi. But you see here that the key difference is that when we want to use linear model to for the expected value, we also need a function g to transform the expectation, right? So this g here is called a link function. And a very nice way to think about the link function is that it just transforms the domain of the problem, right? For example, if yi is Bernoulli distribution, false Bernoulli distribution, right? So this means that the domain of mu I, right? Because this is the expected value of yi. So y can only takes 1 or 0, right? So this is only 1 or 0, right? So the expectation of that is going to be it's in between 0 and 1, right? We'll see here that on the right-hand side, this xi transpose beta belongs to the entire real space. So it means that our function g here, so it needs to map the value between 0 and 1 onto real space, right? So a common choice for that is just going to be the logit function, right? So the logit function can do that, right? So this also means that the G inverse logit for G and then the sigmoid is for G inverse, right? So that's a common choice we use for model Bernoulli distribution. So the point of this link function is just to transform the domain for the expected value onto real space. So now let's compare how do we solve the linear models versus the GLM, right? So actually linear model can be thought of as the maximum likelihood estimation for Gaussian, right? So LM is maximum likelihood for Gaussian. Right, so GLM here is also can be solved with maximum likelihood, right? So it's also must be solved with MLE. But you'll see here the difference is that for the linear model, we can actually solve it in closed form, right? So we got beta hat equals to x transpose x inverse x transpose y, right? So we have the closed form for Gaussian, but for the GLM, we actually don't have that. We can solve it numerically using the IRLS algorithm. It stands for iterative reweighted least square. So that is the numerical algorithm. But the next thing is that the likelihood function for the GLM is convex. So I should say the log likelihood is actually concave, right? It's concave. So that means when we solve it numerically, it has an optimal solution for it. So that is the difference between LM and GLM. Then for our generalized additive models, we're still going to solve the problem with the IRLS algorithm, but we solve it for the penalized likelihood with a curvature penalty. So okay, now I think we are ready to combine the Spline function with the GLM to see how we can define the GAM problem. Okay, finally, for the generalized additive models, we just combine the Spline function with GLM into one framework. So here, the first step is that for the generalized linear model, we can assume yi to be exponential family distribution, right? So you can write out the expectation for yi as mu I. Then we use the link function g to transform the mu I. And then that will be modeled actually with some nonlinear function f of xi. So this is the key for the Spline function to come in. Then for this particular problem, because our xi is p-dimensional vector, so let's just do one more extension here by writing out it as a sum of a bunch of nonlinear functions from the first predictor to the last predictor, right? So x has p dimensions, we can write it out separately for each of the predictors. Then basically for each of the nonlinear function, right, we can actually expand it using our basis expansion formula here. So we can expand it out in this way. Then we can also write out the matrix form, right, such that fj of x equals to phi j of x transpose beta j, right? So then we can also write out the smoothness penalty for each piece of the function, right? So the smoothness or curvature penalty of that's gonna give us beta j transpose omega j beta j, right? So that is the penalty here, and then we also so that is the penalty for each function fj, right? Then for the entire function, we're just gonna sum all the penalty up, right? So the entire function, the penalty, the I should say that penalty for f, that's gonna be the sum of j. Then I'll have the lambda j, and then beta j transpose omega j beta j, right? So that is going to be the penalty for f. So the objective for GAM, so we'll have the likelihood function in the first term. We want to maximize the likelihood function. So so see here that so likelihood function actually coming from the exponential family, right? We just write out the probability for each data point and then take the log for that, right? So that gives us a log likelihood. Then we also want to penalize on it, right? We want to penalize, that means because we are taking the max, so we need to subtract the penalty as summation of j, lambda j, beta j transpose omega j, beta j, right? So that is the objective for the GAM. Okay, so so a very nice thing about this penalty here is that when we take the derivative of this thing, right? So that's gonna give us a very nice form, right? That's gonna give us so the derivative of this term is just gonna give us lambda j times omega j beta j, right? So that's not gonna add lots of complexity to the IRLS algorithm. We'll still have the closed form solution for it for the numerical update when we compute the gradients and for the Newton step, right? So that's very nice. Okay, then the last thing I want to say about the GAM model is that now we have extended the nonlinear curve fitting into a probability framework, right? Into a statistical framework. That means we can perform inference on it. Because for our smoothing spline, if we just solve one objective function there, that means we only get a point estimate, but we don't know the uncertainty of the problem. But you see here, the nice thing is that we are building this GAM model inside this exponential family distribution, right? So that means we can not only know the point estimate for the f, we can also find the variance of f, right? That's something very interesting. So remember that. So here, let's just say this is an inference. All right. So remember that our f of xi, if I just write it out as a full matrix form, that's going to give us, I should put a hat in here, right? It's going to be phi times beta hat, right? So the beta hat here will follow some normal distribution. So the variance for the beta hat is the interesting part because it can tell us the uncertainty of the model, right? So we'll have x transpose wx plus lambda omega inverse, right? So this W here coming from the GLM, it is associated with the variance of the exponential family distribution. So comparing to the GLM, we will just have this lambda omega here as an extra term. So that is due to the penalty, right? That's coming from the smoothness penalty. But the point is that, after we have this variance for beta hat, we can do hypothesis testing on it, right? We can put this give us things like confidence interval or hypothesis testing, right? For example, if we want to find out one particular beta, so let's say that beta I equals to 0, right? We can set that as a null hypothesis. then we can use this variant term to give us a p-value, right? That's really the power of the GAM model, is that we can apply hypothesis testing on nonlinear models, right? So that really goes beyond the smoothing spline, where it just gave us a point estimate of it.